So for this particular module, we had started looking, and this is just an extension of the configuration that we have looked at, where we look at the Newman projections and the chair conformations, and so on and so forth. So in this module, we also started to look at the chiral centers. For chirality, you need to have sp3 atom, 4 different groups on that atom, and a non-symmetric point or plane on that atom. And that would make that particular atom a chiral center. So based on that, we also looked at R and S configurations. So knowing your R and S configurations is a very important part of this particular module. First of all the groups that are associated to that carbon atom or chiral center, you have to look at the atom which is directly attached to that chiral center. Based on the atomic number, you will judge who is going to be the higher priority group. If you cannot judge based on that directly attached atom, you go to the next atom. And there you compare the atomic numbers. Once you have given your priorities, we then give our groups the priority numbers. We have to make sure that our lowest priority, your number 4, has to be at the back. You can do that with models, or you can do that on paper also. But when you're doing it on paper, make sure that the orientations around that chiral center should be kept intact. So if you're looking at this chiral center, you have to make sure that the orientations for the planar bonds, for the dash and the wedge bonds, they should be exactly where they are. Once your number 4 is at the back, you can completely ignore it and just rotate from 1 to 2, 2 to 3, and then back again. This will tell you what is your rotation. And remember, first switch will give you the enantiomer. So whenever you will switch any 2 groups, it will give you its corresponding enantiomer at that chiral site. The second switch that you will make will give you the original molecule. Once you know how to assign R and S configurations, the first relationships that we are studying are the enantiomers. For example, R and S, they are opposites of each other. And similarly, enantiomers, they always exist in opposites, always exist in a pair. Pairs of non-superimposable mirror images. What is a pair? How many are there in a pair? 2 structures are there in a pair. If your conformation is SR for one structure and it is exactly opposite, that is RS for the other structure, you know that these 2 structures will be enantiomeric to each other. Also remember to look at the same carbon. Don't compare carbon 2 with carbon 3 of the other structure. If you're comparing carbon 2 of this structure, make sure that you compare with carbon 2 of the other structure as well. So knowing this, that you have exactly opposite locations of both these structures, you will know that you have an enantiomer at hand. These 2 are mirror images, non-superimposable mirror images. And this is where we bring to our relationships sequence. Whenever you're given 2 structures, first of all, you should be able to see them properly. If you see them better in a wedge or a dash, if you see them better in a sawhorse, however it is easy for you to see. If you want to see them on models, you can do that also. But when you have these 2 structures or any 2 structures, first of all, compare their molecular formula. and their HDI. If their molecular formula and HDI is different, you know that they are unrelated. If their molecular formula and HDI is same, then you will go ahead and look at the connectivity. If there is a difference in connectivity, you can directly say they are constitutional isomers. But if the connectivity is exactly the same, then you check for chirality. If there are no chiral centers, you can just state those two isomers are exactly same. But if a chirality center is there, it is too early for us to say they are the same. If there is a chirality center, assign R or S configuration to each of those chiral centers. And then compare, just like we did in these two structures. And don't be scared. There might be one chiral center, there might be two chiral centers, there might be more chiral centers also. So don't be scared. Just label your structure 1 and then label your structure 2 accordingly. If there are no chiral centers but there are double bonds or rings, also check for cis and trans geometrical isomers. Okay? If your R and S are exactly the same, and remember I flipped the structure, but this is still the carbon 2 where bromine and OH is. Carbon 2 where bromine and OH is. So I compared this S with this site, this S. Whereas this R and this R are exactly the same. So what do I say? What is the relationship between A and B? They are the same compounds. But enantiomers have an opposite relationship, and that's what we were looking at. They will always have exactly opposite configurations. The only issue with enantiomers is we can see them on paper that they are enantiomers. And enantiomers have exactly same physical properties. If the melting point of this compound is 180 degrees, this compound has same chemical connectivities, and hence this compound will also have the same melting point, same boiling point, same density, same physical properties, same chemical properties also. And hence it is very difficult to differentiate or separate our enantiomers. There is a process known as resolution. And I just want to warn you, in your drill, we have a resolution question. You don't have to worry about that resolution question for this course. Resolution helps separate enantiomers from a mixture. And why do we have to do that? And this is something that we will start studying in Module 7, where we will look at racemic mixtures. So after you have known your enantiomers, let's look at our second relationship, which is diastereomer. Now, diastereomers are more common. There are more diastereomers for a structure than there are enantiomers for a structure. So, for example, the structure that we were doing right here, right here. Let's compare another structure here, BrOH, NH2. So if I'm comparing C with E, so this is my new structure. How do I know it's a little different? You can see at their attachments also. So this Br and this OH, Br in the wedge, Br on the wedge. OH at the back, OH at the back. So when we will do the configurations, we will see that this is a R. But in the other chirality center, what do I have? I have an NH2 at the wedge, at the back CH3, and the rest of the molecule. And because we have already figured out this chirality center yesterday, I'm just going to copy it from there, R. So what is the relationship that I see now between C and E at C2 and C3? What is the relationship? For structure C, at 2 I have a S, at 3 I have a R. At 2 I have a S, at 3 I have a R. And for E, what do I have? At carbon 2, 1, 2, 3, 4, 5, I have a R and I have a R. So what is the relationship between these two? This is a SR and this is a RR kind of a molecule. Are these exactly opposites? They are exactly opposite at this end, but this comes here. So a weird combination and not an exactly opposite combination decides that they are not enantiomers, but diastereomers. Diastereomers, there are a few requirements for diastereomers. First of all, you need at least 2 chiral centers for diastereomers. How many chiral centers do you need for an enantiomer? Only one. At least one chiral center needs to be there. There can be more, but for an enantiomer, you need at least one chiral center. So when you have only one chiral center, you know your structures will never be diastereomers. So these diastereomers are always present with at least 2 chiral centers. And now while enantiomers are mirror images, diastereomers are not mirror images. Okay? So this is the thing that you need to know about diastereomers. There is only one other enantiomer, but there are several other diastereomers that can be possible. Any questions? Another structure, another relationship that we see is a meso structure. Now, meso structures and this is just a repetition of what we studied a few minutes ago between diastereomers and enantiomers. A meso structure occurs within the same structure. So within the same structure, you will have achirality. And just like diastereomers, this also needs at least 2 chiral centers. So what is happening here? When we look at this structure, how many chirality centers do you see here? 2. So N is equal to 2. How many stereoisomers are possible? 2 raised to power N, which is 4. And on this Fisher projection, and these are called Fisher projections here, which you are seeing, there are 4 stereoisomers that can be possible. Okay, and they have all switched at least one pair of groups. So in here, between A and B, what do you think has been changed? The H and the OH have been replaced. Okay, and then this H and OH have been replaced. But if you look at this particular example, When I switched this and this was kept intact. Okay, so only one switch occurred here. What about the other one? In here, I only switched this one. And so when I had this structure, oops, I switched here. Okay, so I can make my 4 stereoisomers. Unfortunately, for 2 of them, there exists a internal symmetry or plane of point. Okay, so within the same structure, I have a point or plane of symmetry, and this is what causes a mesostructure to happen. So this is R and this is S. When you will place this molecule in the plane polarized light, half of the R will rotate the light to, let's say, one direction. But the S, because they are exactly same groups, you are mirroring these groups. So they are acting like 2 different enantiomers within the same molecule. So if one rotates the light to minus 30 degrees, the S enantiomer will rotate the light to the same extent but in opposite direction. Remember, that's what enantiomers do. Enantiomers rotate the plane polarized light in exactly to the same extent but in opposite directions. So while your one enantiomer rotates the light to the right, the other enantiomer will try to rotate the light in the exactly opposite direction. What will happen overall? Overall, no rotation will happen. They will cancel out each other's rotations. And this molecule, even though has 2 chiral centers, will be considered as a chiral center. Okay, so achiral and plane of symmetry. So this is what our mesostructures will look like. For this particular compound, there are 4 stereoisomers, but only 2 of them are chiral. If you look, these are mirror images of each other. Can you superimpose them on each other? If you slide this over this, you are going to have OH here and the H here and the H here and this OH right here. So you're going to slide them out. They will not superimpose, and then you can say easily that these are mirror images. Looking at the mirror images in the Fisher projections are quite easy and convenient also. Let's look at more examples of mesostructures, meso and other structures. Let's see if we can figure them out. So I'm going to draw a Howard projection, and if you remember, Howard projections look something like this. And I have a group going up and down, up and down. So Cl, Cl, CH3, CH3. Definitely a chiral center. This group, this part of the ring and this part of the ring are different. So on this chiral carbon, you have 4 different groups. What about this? Yes, definitely chiral. This group is different from this group. This part of the ring is definitely different from that part of the ring. However, if you notice, there is a plane of symmetry. And so we can say that this molecule is a meso structure. On the other hand, if we similarly have the same groups, another stereoisomer of this molecule, chlorine and CH3 are where they are, but I switch one group, CH3Cl. Now, is there a plane of symmetry present? No, it's not. And so this structure will probably not be a meso structure. Okay, it can exist as an enantiomer, but not as a meso structure. Similarly, this is achiral, meso, and this is a chiral structure. And you have more to see in your drill manual also. So Fisher projection, as we were seeing, is a shorthand notation of depicting the long chains of carbon, and usually we use them in sugars. By rule, the most oxidized, which could be a carboxylic acid, it could be an aldehyde, it could be a ketone also. So most oxidized carbon, which has the most number of carbons, what does carboxylic look like? 2 double bonds with the oxygen, and then this. So 1, 2, 3 oxygens, you can say. With an aldehyde, what do you have? 2 oxygens and 1 hydrogen, and then rest of that molecule and this carbon. So most oxidized carbon is usually at the top, whereas least oxidized will be at the bottom. So if you look at models, how do we see our So just imagine the red group is my carboxylic acid, and this red group is my other CH2OH. And I'm placing these two. This is a tetrahedral molecule. I'm placing them like this. You can also think about Fisher projections as a friend. You know, this is a friend who's coming out to you to hug you. So both the hands or both the side arms are coming out, while the backbone, this backbone spine, is going at the back. So when you're looking at R and S configurations for this particular carbon, remember both of these side arms are coming out, while the top and the bottom part is going at the back. Another view of looking at our molecule. So this is a sideways, this is your sawhorse, this is your Newman, and this is your Fisher projection. Okay, just different ways of seeing the same molecule. So let's do one example here. And some people also think that this is like a bow and tie, which is also perfect to think about. CH2OH, HOH, NH2, H. Okay, we are almost done. I just wanted to finish a few more examples before we call it a day today. So how will I go about this? I will have to look at this carbon and all the 4 groups around it. I'm going to make the same orientation as I have to. Looking at this group, which is the biggest group on this? This is atom A, this carbon is atom A, this carbon is atom A, and then this carbon is atom A. Among all of these 4 atoms that are directly attached to my carbon of interest, I see that this hydrogen will be my number 4 because of the lowest atomic number. Between all the rest of these 3, I see that this carbon, the next atom on this carbon, atom B, what is on this carbon? I have 2 oxygens and 1 hydrogen. What do I have on this carbon? I have 3 hydrogens. What do I have on this carbon? I have 1 oxygen, 1 carbon, 1 hydrogen. 1 oxygen, 1 carbon, 1 hydrogen. Do you see what do I have on this carbon? And out of these 3 situations, this part will be my priority 1. This part is my priority 2, and this part is my priority 3. So I can either take my baby steps and make my 2 other structures so I can look at it carefully. What would I do? I would want to keep my 4 at the back. Where do I take my 4 at the back? I can take it either locations. So I can take it here and then switch these 2. Since my number 4 is at the back, I just have to make 2 other switches. Oh, I already did those. 2 and 3. And so ignoring my number 4, I will go from 1 to 2 to 3 to 1. This is a anti-clockwise motion. And so this is a S configuration, right? Let me do this third one also for you. So this third one, what do I have here? This group going up, this group coming down, sideways bonds, and I'm going to assign my priorities here. This is my atom A. For this carbon, this is also atom A. And this is atom A, this is atom A. Between nitrogens, carbons, and hydrogens, hydrogen is going to be my number 4. NH2 is going to be my number 1. Between these 2, this carbon has 1 oxygen, 1 hydrogen, 1 carbon. So matches this. Whereas this carbon has 2 hydrogens and 1 oxygen. So 1 oxygen and 1 oxygen cancel here. 1 hydrogen and 1 hydrogen cancel here. So between a hydrogen and a carbon, this group will be more priority. So this is going to be my number 2. This is going to be my number 3. And just remembering my part where I have 4 and 2, 3 and 1. So I switch these 2. And then as my second switch, I switch these 2 also. Ignoring number 4. 1 goes to 2, 2 goes to 3, 3 goes to 1. What kind of a rotation is this? Clockwise. And so at this carbon, it will be a R. What would happen to this carbon? There is this group, there is this group, there is this OH, and then there is this H. And so when I will figure out the configuration, it would come out to be a S. You can do this on your own to figure out. What if I ask you to find relationship between these 2 structures? structure X and structure Y. These two, both of them, look a little different, right? A lot different actually. This looks like a Fisher projection. This looks like the side wedge and the bond kind of a structure. So what would be the relationship between these two? So we are going to do our technique again. We are going to find out the molecular formula. Then you look at the HDI connectivities. We see all of that is exactly the same. Are there chiral centers? Yes, there are chiral centers right here. And then there are double bonds. We do see double bonds, but that will be part of your functional group. You cannot assume that they are alkene with cis and trans kind for double bond. Can anybody tell me what is this functional group? Anybody? This
Is it a carboxylic acid?
a carboxylic acid would look something like this. So this is a aldehyde, but it is a carbonyl group. Yes, you're right. And so it's exactly same connectivity. What is the next step that we have to do? We have to figure out the R and S configurations here. So if this is carbon 1, where is my longest chain? I will have to make sure that my longest chain is there. The priority group, the functional group, which is the most important among hydroxide, amines, and aldehydes, it is the aldehyde which is the functional group for priority. And that is the one that should be present here, included in the longest chain. So 1, 2, 3, 4, 5. I have this long 5-member chain. You don't need to know the name of the structure, just the numbering. 1, 2, 3, 4, 5. Okay. Oh, I have to draw the OH also here. So this OH right here. And so when I will do the configurations at each of these, I have to know and remember on this very carbon, how many bonds do I have? 1, 2, 3. What is this group? A methyl group. Do I only have 3 bonds on this carbon or do I have 4? Can anybody tell me that? Anybody? So there are 4 bonds. The 4th bond, which will be away from this bond, will be the hydrogen that we talk about. On this 3rd carbon, how many bonds do I see? I see 1, 2, and 3. Do I have a 4th bond? Yes, I do. And that is my hydrogen here. What about this? Yes, I have a hydrogen here also, a hidden hydrogen. If my group is coming out, my hidden hydrogen will be going back. And so when we will do the R and S configurations, what about this carbon? Is this carbon chiral? It is not chiral because both the groups hidden here are hydrogens. And that is the first requirement of a chiral center. Your atom has to be sp3 hybridized and all the 4 electron densities around it or the electron domains around it must be different. So this is one of the questions that I would like all of you to do. Now the last combination or this type of structures that we see are racemic mixtures. Racemic mixtures, just like your mesostructures, are achiral. Unlike your mesostructures are within the same molecule. Racemic mixture is 50% one enantiomer plus 50% of other enantiomer. So there are two pure molecules, pure one enantiomer, pure another enantiomer, and then you mix them together. 50-50 in a solution. That's when you get racemic mixtures. If one enantiomer rotates the light in one direction, the other enantiomer rotates the light in exactly same extent but opposite direction. And so racemic mixtures are also achiral. Okay, so there are two different structures. Meso compounds, it is the same structure, within the same structure. When you're looking at Fisher projections, I also want to, or any structure for that matter of fact, I want to warn you. Sometimes we do a rotation. When I do a rotation, I'm rotating A, I'm rotating C, I'm rotating B and the D. So I have just rotated the molecule. But when I'm making a switch, that's the time I am making a stereoisomer. So same. What is the relationship between these two? They are same structures. One switch, when I do that, I keep my A where it is, I keep my B where it is. And I just switch C and D. Now I have created enantiomers. So I've already assigned you one structure. I want you to look at this Newman projection also. Which? But some days if I'm not able to see my Sawhurst Newman, I can just convert it into FHCH3. I want to draw my F. So I'm looking in the front. From my front, CH3 is on my right hand side, so it will come out. H is going back. Now this H is going down. This CH3 will be coming out. This OH will go back. So you can also do this on your own. If you're looking at the frontal carbon and you want to draw this carbon right here, what do? You just divide them. Everything here will be coming out. Everything here will be going at the back. Okay, just remember the direction. This is going up and back, up and back. So I can see this much better and I can assign them. This will be 1, 2, 3, S. And this will be 1, 2, 3. So this will be 1, 2, 3, and 4, S. So this is, I can see this better than I see that. If you can see this also, then that's perfect. Remember this carbon and that carbon. To this carbon, that carbon is going at the back. To this carbon is coming in the front. It's just the way you are viewing it. So what if I give you this structure and ask you, what is the relationship between these two structures? So will you be scared? Yeah, a little, that's fine. But first, check the molecular formula for both of these. What is the molecular formula for this? What is the molecular formula for that? And then figure out if the connectivity is exactly the same on the first carbon. So if I have this carbon, because this is a priority, I will start counting closer to here. 1, 2, 3, and 4. On the second carbon, I have a OH. On the second carbon, I have a H. So on the second carbon, 1, 2, 3, 4. So here is my longest chain here. On my fourth carbon is by itself. Third carbon has a fluorine and a hydrogen. Third carbon has a fluorine and a hydrogen. So exactly same connectivity. What is the next step that I have to do? I have to look at the chiral centers. Do I have chiral centers here? If yes, then I have to assign them the R and S. So I'm using the same sequence. Oops, my bad, wrong number. Okay, right here. I'm using the same sequence here. Molecular formula, then connectivity. And how do we assign connectivity? You have to know your module 4 nomenclature, longest chain. Longest chain must have priority. Longest chain must have all the substituents, more substituents. And that's when how I'm numbering my structures. Once you have figured out your longest chain, then you give the lowest locant value also. So this is your previous information that you have to remember. Once the connectivity is exactly the same, then you assign R and S. Remember, for your Fisher projections, everything on the spine is going at the back. Everything on the sides is coming out at you. And so when I will do my chirality centers, yes, this is chiral, yes, this is chiral, yes, this is chiral, and this is chiral as well. And so I can do my 1, 2, 3, 4. So this is my S. And here 1, 2, 3, and 4. 1, 2, 3, 4 R. Okay, and of course it'll take you some time, but you will come here one day. Okay, that you can just look at the groups and then you can rotate them accordingly. But for now, take baby steps, and that's completely agreeable. I know it's some of the students can see it better. Some of the students like me, I still have to draw them and look at them differently. Okay, so don't feel bad. So now I have to compare my same carbons. And let me label this as P and Q. Structure P. What is at C2? It's a S. What is at C3? It's a S as well. At Q, what is at C2? It's a S. What is at C3? It's a R. So what is my combination? I have a SS compared to a SR. Is the, I'm sorry, SS and SR. So at my P, all these configurations, are they equal and opposite to that of R at the Q? They are not. Are these two enantiomers? Anybody? When you have a combination like this, will these two be enantiomers? They will not be enantiomers. If they were enantiomers, you must see a completely opposite combination. So for every SS enantiomeric pair, there has to be a RR structure. For every SR pair, there has to be a RS kind of a pair. So at all chiral centers, you have to compare And at the same chiral centers, you have to compare. If it is exactly the opposites, then you have an enantiomer. If there is a weird combination, then it is a diastereomer. So now tell me, what is the relationship between P and Q? Is it enantiomer, diastereomer? Nothing? Okay. It is a diastereomer. Okay, just to kill the suspense, I'm going to tell you the configuration of our other structure also, which we're doing here. So at this carbon, I will have a S. At this carbon, I also have a S. And at this carbon, I have a R. So S, S, R, exactly same. S, S, R. What is the relationship between these two? These two are exactly same structures. So that is the relationship. Okay. So this will conclude our chapter for module 6. I just wanted to remind you that knowing your relationships between two structures is going to be very, very important. Please make sure that you follow the sequence. If you have your own way of doing a sequence, that's completely fine with me also. And these sequences are also available on your sequence sheets, the other sheets that I have made for you. But please make sure that you practice these, especially assigning R and S configurations, knowing the relationships between two structures, and so on and so forth. Okay.